Hello and welcome everyone. My name is Peter Robinson. This is the Ethereum Engineering Group meetup. So today I'm going to give a talk on something that's come in recently in the Prague hard fork of Ethereum. And it's something that offers great opportunities, but there are some real gotchas there too. So relevant to not only people who are developers, but anyone who actually uses the chain and signs transactions, which is a darn lot of people. So I will share my screen in just a sec. Let's go share. That's the one. Share that. Okay, and let's drag you all back over to here. And I'm not going to be able to see chat, I think. Oh, maybe I will. Yep, right. Let's have chat off to the corner here. Yes, so I'm going to talk about smart accounts. And so let's dive into it. So as I said, EIP 7702 allows externally owned accounts to become smart contract and to have smart contract logic directly from their own address. And so gives them great power to do great things. But you've really got to watch out for, there's adding complexity and also the security considerations. But this is one of these upgrades that is just happening. And so you can't choose to say, oh, I'm going to bury my head in the sand on this one. This is something you've got to know about. So let's walk through the use cases that this is designed for. So it's aimed at a whole ton of things, of which one thing I think it was originally aimed at early on, it doesn't actually fulfill. But so in a normal flow, you're going to have an app, say Uniswap or something like that, some other app out there, and you want it to be able to do stuff with your tokens. And so you end up submitting a transaction, say, hey, I approve that app to do something. And then you submit another transaction to say, do something. And then it will invariably do a transfer from on that token. And so the spender there is going to be the app that you're wanting to approve to do stuff. And the value could just be the amount that you need to be spending, but usually it's set to infinite, which has got pretty big security issues because if the spender has infinite approval, say on an ERC20, that means that maybe in that single transaction they spend, say, $10, say. But if you've given it approval for all and you've got $1,000 in your account or in that ERC20, then that could be drained later on if the app gets hacked. And this sort of thing's happened before. So there are actually websites you can go to check which apps you've given infinite approval for, and you can revoke that approval. So, yeah, and then do stuff calls the app's logic, and which in turn calls transfer from. And so if you're using EIP 7702, then you've got this smart account, which is a contract operating at your address. And so you will just submit a transaction which has got essentially messages in it saying, can you do approve? And then can you call do stuff? And it'll go off and do those calls. And the message sender that everyone's seeing here is the smart account, which is the same address as the EOA. So it says if Alice here is actually submitting those transactions individually from her smart account. Another use case, which is similar but different, is doing a multi-call. And so this is where you want to say, call transfer to transfer some money to Alice and then transfer some money to Carol. And, you could do these two transactions, but another thing you could do is you could deploy a multi-call contract. And then, you deploy the contract and then you use it. Issue, of course, with this is that, sure, the people on this call are technologically savvy enough to deploy a multi-call contract, but Joe Public can't do this. It's beyond their capability set. And so, it's putting a huge bar in the way. So that's not a good real thing that people can do. So a better way of doing it is to again use this sort of feature where you submit a bundle of transactions. You say, can you call transfer to Alice, then transfer to Carol, and then it happens. Another big thing that this allows is integration with account abstraction and gas sponsorship. So EIP 4337, which I might have that number wrong. Anyway, so the that allows you to do submit to a bundler, and then from the bundler then submits your transactions to an entry point contract that then calls the smart account, and you can use a paymaster to do the gas sponsorship. And another use case that we've got is limited access delegation. And so imagine you've got an app, and what you want to do is you want to let it buy from a marketplace some token, some ERC 1155 NFT for an amount of money. And you want it to do it, say, when the market is at a certain point, or maybe you want to do it each day or something like that. And so you could, with a smart account, you could give it access to do that. And then the app can use your account to do that limited set of things. And then another similar thing is that you could just hand over capability for an app to do stuff, but only with a certain contract. So maybe you're using a game, and in the game, there are a few game contracts. And so you're allowing the game's service to do whatever it needs to do whilst you're playing the game to give you the in-game experience, but still being a Web3 game. You could also imagine a subscription service. So imagine a service where each edition of a publication is represented by an NFT. So as far as the access to it is represented by an NFT. And so similar to how in the good old days you could buy a magazine and maybe you could give it to someone else after you've read it, this would allow you to say each day, buy the latest edition of the magazine, the NFT, so you've got access. But then later on, you could trade that NFT and sell it to someone else. So another use case is asset recovery. And so, we've all heard about people who lose their private key or they lose access to it. And so if you had a recovery service where you did, say, lots of authentication, probably hopefully more than mother's maiden name, but, some sort of recovery situation, it then talks to some recovery contract, which then engages with your smart contract. And then it allows you to maybe transfer all of your assets that you've got, your, ERC 20, 721s, 1155s to a new account. And so allows you to recover your assets. Yet another use case is dynamic allow list. And so in this case, what it's about is that you want to have a contract which is only allowed to interact with a approved set of other contracts. And so this could be maybe some wallet that you really want to lock down, or something along those lines where you're saying, look, we're happy for this wallet to interact with these accounts here, but no other accounts. So, you could imagine that sort of thing. One thing that I think with account abstraction and this had been hoped for is to allow different types of authentication. So rather than just ECDSA. And so this is actually from the Australian Signals Directorate. They've been looking at, well, what happens with quantum cryptography, and how is it going to affect things in the like classical crypto world. And so if you look here, they're saying that, like there's going to be a cryptographically relevant quantum computer. So something that really could break stuff, break all the encryption currently used on the internet pretty much, by about 2030. So all of the asymmetric algorithms, so like ECDSA and RSA. And so they're saying, it's plausible that it could happen in 2030, but far more likely that it's 2040. And so what they've got here is they're saying, well, even before you get a quantum computer, you're going to have like all sorts of organizations around the world that'll be sucking up data and storing it for later decryption once they get the tools to decrypt it. So they're saying that, really that could be happening, say in 2027, you could have something that's still relevant by the time you've got one of these quantum computers that could break crypto. So for a lot of what we do in Ethereum and associated chains, it's really not that big a deal as far as encryption goes, because usually what we doing is we're signing things and not encrypting. So I think the shaded area for a lot of blockchain applications is less relevant. However, signing's super important, because that's how you sign a transaction to say, I want to move money from my account to someone else's account. And so being able to have a quantum computer resistant algorithm would be really good, and having a way of having it on Ethereum would be really good. And so, you could imagine that you could have like sign a transaction with an EOA with a normal private key, normal ECDSA, and then you could sign a message with some extra quantum computing resistant algorithm. And that'd be, ideal. But unfortunately, this doesn't work. And the reason why this doesn't work is that the EIP 7702 architecture still allows you to use the ECDSA to essentially switch smart account code. And so you could have all the code you like in your current smart account, which could be post-quantum computing, good, but then you might switch. So I have gone through the use cases lightning fast. Are there any questions about those use cases?
Peter, there is one more ERC 77701. What is the difference between these two?
Ooh, I don't know. I didn't look. I've looked up about what feels like 100 EIPs whilst putting this talk together, but I didn't hit 7701. Let's very quickly find out. Okay.
It's a native account abstraction.
Yeah,
This actually came before, but it is not yet implemented.
Yeah, and so I think that you will find that native account abstraction, so if we had native account abstraction, you could imagine that this use case would work. So at the moment, my guess is, so I haven't looked into that EIP. My guess is that that isn't going to come up for any time soon. I think that there is the Ethereum object format stuff and other things like that that'll happen as far as the EVM space is concerned. And I think this 7702 as far as we're going to get for a while. That's my guess.
7702 is right now available, right?
It is. It's in Pectra. So as of
Pectra,
May, yeah, as of May.
So anybody implemented these use cases in production?
Yes. Now, later in the talk, I'm going to go through and talk about adoption. So talk about who's using them and for what.
Okay, sure. Thank you.
Yeah, it's okay. Thank you. Are there any other questions?
Peter, are you there?
Yeah, hi.
Hi, it's Barry Easman here.
Yeah.
Hi.
Hello.
That chart you were looking at just before with the cryptographic vulnerability.
Yeah.
So were you saying that that's really referring to the ability for a quantum computer to decrypt encrypted stuff, and therefore not as relevant to signing?
I'm saying that it's so what I'm saying is that this grayed out, or this, I don't know, not sure what color you'd call that. It's not orange, but it's not anyway, whatever color that is. Peach, maybe? Yeah, that peach colored area. The idea is that all right, you're at Laborus. So imagine Laborus has got some secret confidential company information that is encrypted. And so someone, I don't know, CIA, I don't know, Russian spies, Chinese spies, anyway, someone hacks in and steals all your data. So currently it's encrypted and they can't do anything with it. So in the 2030s or maybe 40s, they could decrypt it. And so what the ASD is saying is, well, it might still be relevant information, because obviously like in 10 years time doesn't really matter, no one cares. So as far as signing that goes though, you don't have to worry about this peach colored area, and it's really once you've actually got a computer that can do the stuff, because then what we do is we say, all right, Barry's we've seen Barry use his public key. So he's signed something, he's done a transaction, so we can work out his public key. And now what we're going to do is we're going to reverse that to work out the private key, and then we're going to sign a transaction. They'll probably go for Satoshi Nakamoto's Bitcoin private key, I dare say, and not your one, because he's got a little bit more money. But yeah, so that's only going to be relevant once a quantum computer's available. But
Okay, so it's just as vulnerable, but what you're saying is that because signatures tend to be fleeting, only relevant for fleeting periods of time, and generally aren't stored for long periods of time, then that's less relevant.
Yeah, that's exactly it. So
but if you did want to save a signature for a long time, then it would be just as vulnerable as any other encrypted data.
Yeah. And so, for instance, you could imagine you might have assigned an encrypted blob of information to say, I don't know, I did this at a certain time. That might be why you've signed and encrypted something. And so obviously, if someone can forge your signature on something that supposedly was signed in 2025, in 2035, then it means that, well, is that signature valid or not? You're not going to know because someone could have forged it.
Yeah, cool. All right, good. Thank you.
No problem. All right, I'll keep on going. So let's talk about the architecture now. And so Alice has this smart account, which is at her EOA address, and she delegates. So she uses the code in an authority template contract. And so the authority template contract, it's just deployed like any other contract, and it can do anything. There are no rules. It's just a contract. And to delegate to that template contract, you just call a set code transaction. So this, I've said set code instruction, but it's actually a set code transaction. And so you submit one of those transactions, and in it you specify that authority template contract. And to change your delegation, because you've decided you want to use a different authority, a different template, maybe you're upgrading, you call set code again. So you submit another set code transaction. And to cancel your delegation, because you've decided that you don't like EIP 7702, you specify 0 address when you're calling set code. And so importantly, though, set code doesn't alter storage. So it's just pointing at some code, but it's not actually changing the storage slot. So your EOA now has storage, and like submitting a set code doesn't change anything. And another thing to think about is that you start using that code, but there's no init code. There's no constructor that you're calling. It's just there that already deployed. So it means that you need to be able to use it without having to have some constructor run. And so the set code transaction looks like this. And so all these bits, these fields here are just the normal fields, except for authorization list. And so authorization list is an array of chain ID, address, nonce, and a signature. And the signature of this transaction is the hash of the type of transaction, which is type 4, and this RLP encoded payload. And so you've got a list or an array of these authorizations. And so the idea is that you could have some sort of bundler submit this array of delegations on behalf of a whole heap of EOAs. So you could submit it on behalf of your own EOA, or you could have a bundler submit a whole heap of them all in one go. And so the chain ID could be 0, which means this will work on any chain, or it could be the chain ID of the current chain, and which means that this authorization is only relevant to the current chain. And so the address is the authority template contract that you're pointing at. And the nonce is just a normal account nonce. So just like when you're signing transactions, this is the EOA's nonce. And then the signature is, is created by signing, using your private key. So it's going to resolve to the EOA's address. So it's saying that this authorization for this chain to this template is for the account, which will resolve based on this signature. And so you could imagine, in a big long list of these authorizations, someone might mistakenly put multiple authorizations for the same account. If they do, it's just whichever one's the last one. Also, maybe someone puts an authorization in your chain ID 1, Ethereum, and they put it in for chain ID 2. So in that case, it'd fail because it's the wrong chain. Or maybe the elliptic curve maths doesn't work out. So not every combination of the Y, R, and S will resolve to a real address. Sometimes the elliptic curve maths doesn't work. And if it doesn't work, then again, this fails. So if one essentially row in this array fails, you just ignore it. You just skip it. So another interesting case is if an EOA submits one of these set code transactions themselves, then what's happening is that you've got 2 nonces and not 1. So one of the nonces is the normal transaction nonce, which has to be the next nonce up. And then you've got this authorization nonce, which is the one after the transaction nonce. So it's essentially the current nonce plus 1. So yeah, something to think about if you're submitting your own one. And when you look at the code for one of these smart accounts, they've got 0xEF0100 concatenated with the address of the authority template. And so it means that if you go get code for an account, if its length is 23 bytes, so 20 bytes for the address and 3 bytes for this prefix, and the first bytes are 0xEF0100, then you know it's a smart account. And so EF is specified in EIP 3541, and it essentially says this is reserved for special stuff. And so Ethereum clients normally reject anyone who's trying to deploy code that starts with EF. And so at the moment, you've got two usages of it. One is in Ethereum object format, which hasn't currently been deployed yet, but they've reserved EF00, and then you've got the next field is version. And then smart accounts are zero, like EF01, and they've got their initial version as 0. So when you're submitting a transaction from a smart account, it feels like it's an EOA. So that means like the transaction origin is the smart account. And that applies even if a bundler has submitted the transaction. So, it's a way of fooling essentially the whole Ethereum ecosystem into thinking that the smart account is operating all by itself as if it's an EOA. But it could be a bundler submitting the transactions. So I've gone through the architecture, and other questions about that? Okay. Yeah. All right. So I looked at about a dozen different examples on the internet and banged together my own one, which I've put into the Meetups GitHub repo. And so how I've started out my code is like this. So it's just a contract at a specific address. So normally the storage layout starts at 0 for contracts, but as of a recent Solidity version 29, you can specify the actual starting offset. And this is useful if you're in this situation where you might have multiple versions of a contract, like interacting, and you don't want to make sure there's no collisions. And so, you would choose your very own starting offset. And I defined a call structure, which, indicates a call that you want to do. And there's a nonce, which I defined for replay protection. And so if an EOA submits a transaction, it would call execute and provide an array of those calls. And the authentication you do is just make sure that message sender is this address. So essentially saying the only thing that can call this is something that's got this address, which would be the EOA. And then execute batch just grabs the nonce, increments it, and then runs through and does all the calls. And then all the calls are just normal, simple calling. Nothing too dramatic there. And also you need to have a receive so that you can accept ETH, so people can transfer ETH to you. But then you might also have a bundler that submits transactions. So essentially you off-chain sign the calls. And so what it does is it gets all the calls, and it ABI encodes them and ends up creating an encoded calls, which is essentially just a linearization, a flattening of the call structure. And then you combining with the nonce, you come up with a digest, and then you work out whether the account has signed that. So whether the EOA signed that digest, and assuming it has, then you should recover to the address. And if you do, then you execute the batch. So that's how you could have batch transactions from some sort of bundling service. So that's a pretty simple implementation, and it's one of those things that I did that before I looked at MetaMask's implementation. And so I learned an awful lot by looking at how they did it. And so their code is deployed to here. And there's also, here's the GitHub repo with the MetaMask code for this. But before I dive in, when I was researching, I came across this really interesting post by Mislav Yavor from Bioeconomy. And so, as he says, a crucial thing to understand is that EIP 7702 is controlled by wallets and not applications. So if you're developing an application, you've pretty much got to give away the idea that you're going to be creating your own 7702 wallet. Because, and the reason for it is actually quite useful to understand, and that is that each wallet is going to have its own smart account implementation. They're not going to trust anyone else's implementation, so they're not going to let you deploy an implementation. And so, you know, it means that you're going to end up having a little bit of fragmentation, so different implementations by different wallets, which will have different capabilities. So it will make things more complicated for applications. But there have been some EIPs and ERCs that have helped this, I think. But it's certainly worth really understanding that it's going to be MetaMask and the likes of MetaMask deploying 7702 contracts and not application developers. So how MetaMask has put it together is that you've got this stateless delegator, and it points to a ERC 4337 entry point. And it also points to a delegation manager, which is related to 7710. And so the 4337 gives you account abstraction, and the 7710 is all that subscription service, limited access delegation stuff. And yeah, so though they have the entry point stuff, one of the things with that is that if you want to use that as with paymasters and you want to use this account abstraction, then you've got to have a relayer service submitting transactions on the chain. But MetaMask works on a lot of chains, and they don't necessarily have these relayers submitting transactions on all chains. So another way of doing it that they've come up with is that they'll submit a transaction to pre-fund an account with some ETH or whatever the native token is on the chain. The account then submits a multi-call transaction to do the things they're going to do. And then they have MetaMask put an extra one in, which is essentially that the account pays for the gas using, say, USDC or whatever token they've got. And so it's a way of doing all the multi-call stuff, even if you don't have the native token and without MetaMask having to run a relayer. So in the contract they've got a name, domain version, and a contract version. So what this is telling you is they've obviously going to use 712, EIP 712, to do the signing. And the version's an interesting one. So that, it really tells you, hey, there's more than one version of this. At some point, there's going to be version 2. And so having different versions is important because it means that, they're thinking that you're going to upgrade this contract. And so essentially you're going to sign a delegation for 1.3, and then maybe next year they'll release 1.4. And next time you go to use your MetaMask, they'll say, hey, you should sign this, or before we let you do anything else, you need to sign this to upgrade. And so, yeah, I think that's a really powerful feature to allow wallets to upgrade their functionality. And so you've got a constructor that takes a delegation manager and an entry point, which we talked about before. So subscription service sort of stuff and account abstraction sort of stuff. And they've also got something for validating a signature as well, which is just making sure for this type of contract that essentially you can recover a signature and say, yes, this is the account that submitted it. And then if you look at the delegator uses delegator core. And so this has a lot of inputs that are really interesting to understand. And so the execution helper is actually from ERC 7579. And so this has got a standardized set of executor types and code to actually execute calls. So rather than reinventing the wheel, they're just importing this. So this has actually got the code as a reference implementation, which MetaMask are using. So whereas I defined my call object and had, execute functions and all that sort of stuff, this defines it for them. And then you've got this 7821 defines a batch calling interface. And then you have a ERC 721 and 115 receiver. And so that's to allow you to receive NFTs. So when you're doing a transfer with NFTs, it says, is the receiver a contract? And if it is, then it calls an on NFT receiver function essentially, which says, hey, can you accept these NFTs or are they going to be lost forever? And so hence, because this is a contract, it needs to implement them. And then, as I said, it does 712, which is that typed signature standard. The delegation manager and entry point are immutable. So that means once they get set in the constructor, they're never going to be changed. And so say if there's a bug in the delegation manager or the entry point code, the only way to fix this is MetaMask updating the this template contract with new, pointing to new versions. So that's an interesting thing to consider all by itself. There's an execute function, which is saying entry point, so the ERC 4337 entry point or self. So you can sign it yourself, or you can have a delegation manager, or not a delegation manager, a relayer calling. And then it's also got an execute function. So this one just had a simple execute object from that standard 7579. But as well, it takes bytes and a mode. And so the mode this gives you more control. You can say, well, we're executing a batch, or we're executing a single call. And then you've got execution type as well, which is in this mode. An execution type can be, hey, I just want to try it, do a trial execution. I don't want to do a real execution of this call. And then the call, if it's a batch, then it unpacks to an array of encryption objects. Otherwise, it's just one encryption object. Execution object, should I say. And then you've got the delegation manager can do the same stuff. And then there's this function and a whole set of other functions. So this is ERC 4337 related. And one interesting thing to look at that I got caught up on for a while was that, the entry point can call it, or only as proxy. So only as proxy is about saying, look, if someone calls this and they're actually calling the template contract itself rather than a smart account, then we should fail. Because, we want to make sure that this is essentially not calling the template account's address, which is an interesting thing to make sure that the template account doesn't end up doing authorizations or doesn't end up receiving ERC 721s or 1155s. And so there's a lot of other functions which are related to enabling, disabling the delegation manager or receiving funds or account abstraction. So a big thing of interest is that this delegator is stateless. And so you might remember in my example, I had a nonce. And if you think about it, though, if you're the EOA submitting a transaction, you've already got your account nonce, which is going to make sure that things are being executed in order and aren't being replayed. But for account abstraction, you do need a nonce. And so how they do that is they actually have the entry point contract hold the nonce. And so it's still being held, but it's being held in the map of the entry point contract. So it means that, maybe they can upgrade and do things without having to worry about any state inside of a smart contract account. And they don't have to worry about an attack wallet somehow or other modifying their state. Okay, security. Oh, does anyone have any questions before we move to security on MetaMask's implementation? Okay. So if I specify chain ID 0, then it allows, the delegation can be, like used on any chain. And so, if you sign a delegation for XYZ wallet with nonce 5, say, and the wallet has a bug, they upgrade, and then, so then the attacker and everyone else is going to know about that bug because it's been fixed. But, on Ethereum, you've upgraded to 2.0, but say on Polygon POS, you might, like not have the wallet deployed at all, but maybe you deploy it, or maybe you have an EOA on Polygon. And so on with that EOA on Polygon, maybe someone will somehow or other, like if you replay that that deployment. So if you're up to nonce 4, and then they can then use nonce 5 to then deploy the wallet, the delegation to the template, to the version 1, which has got a bug. So I reckon that you want to be really careful then not to sign delegations for 0 for all chains and just sign them for a specific chain. It feels far more secure. So there's no constructor or a init code. And so some wallets might consider having an initialize function. But, like if you have initialize, then someone could front run it. And so, like I think having a stateless wallet like MetaMask is a good, or having state auto initialize where, like it defaults to 0, and that has meaning. Otherwise, maybe have an access control function for the initialize and have the wallet itself, so the wallet owner being the one who initializes the account, something like that maybe. But, I think having a stateless wallet seems like a really good idea. So the storage isn't wiped when you change your delegation. And so, you could imagine you can have storage collisions, which could be mistaken or could be on purpose by someone trying to hack the wallet somehow. And so, there are a few mitigations for this. So one is to review the new delegation, so renew the new template contract. But, like I think the people on this call might be qualified to do that, but 99.99% of the world's population isn't going to be qualified to review a delegation contract. So maybe the answer is create a new EOA, or maybe just lock yourself in and say, I'm using MetaMask or I'm using some other wallet, and I'm going to, like just stay with that wallet forever. Maybe. So, so MetaMask is stateless, but Ambire, it stores stuff at a certain address. So yeah, I think you can't just assume everything's stateless. So if you are considering writing a template contract, writing your own wallet, I wouldn't, like you could have mine as an interesting thought point, but mine's not audited. And in fact, looking at the examples I found out there on the internet, there are a lot of bugs in them, including access control, where one of them allowed anyone to submit transactions from your account, which is pretty dodgy. So, you want to, if you were going to do it, review your code, test all the failure cases, have it audited by multiple people. And so what happens if you sign a malicious delegation by mistake? So, you could sign a contract that's going to drain everything out of your wallet. And that'd be a bit of a disaster. So my thought is use a wallet that is EIP 7702 aware, because they're going to block delegations that aren't for their own 7702. But like if something doesn't support 7702, then maybe it's not even 7702 aware, and maybe it might sign a delegation to a malicious wallet, which would be bad. So yeah, you want to be super careful. And with that, let's just dive into looking at adoption, because I think that was a question from earlier, and it really does inform this last thing about malicious usage. So the same people who do L2 beat have done wallet beat, and it looks at what type of wallet they are and do they support 7702, and just talk about so you can click on them to find out more information about them. And so that's a good reasonably easy to comprehend website, which I recommend. Another one, so Wintermute is a bug research place that I think they also do audits. And so it's looking at adoption. And if you look at it, this graph here, so they've got retail wallets have got this much, criminal ones have got this much. So there are more criminal wallets than there are retail wallets, which is not good, not a good starting point. And so then there are some that are uncategorized, so people maybe don't know what those wallets are. But yeah, not a good place to be in. So if you look at the wallets, so you've got Ambire, which we'll go through in a sec, and then you've got this Crime Enjoyer 2, MetaMask, and even different versions of this hack wallet, which is pretty scary. So if you go to Ambire, so click and open that, then you can look at its code, and then you get to see where that it's storing stuff at a certain position. And then if you go into the code here down further, you can get to see where it stores stuff. So you can have a little look at it. If you look at Crime Enjoyer, which is, if you look at it, it's got it's the second most deployed EIP 7702, which is pretty scary. So Crime Enjoyer is really badly written. So essentially anyone can call initialize on this wallet and set up the destination to be their own address. So anyone can. There's no access control. As long as you don't set it to address 0, you're all good. And then when someone receives some ETH, then what it will do is it'll transfer the newly received ETH to the destination wallet. And so, which is it's really strange. Like you could imagine this could be an immutable value, and or it could be a value that you can only change via access control. But generally you'd have it as immutable, and you could imagine that like you could have functions to drain ERC20s and 721s. Not only drain ETH that's coming in, but drain existing ETH. So it just seems incredible. So obviously the hackers didn't upload this code. This has actually been uploaded by Wintermute themselves, I think. And so, yeah, so it's incredible. And if you look at the transactions, you've got all these people over time have been submitting initialize, saying, hey, let me be the owner of it. And then specifying the address. But I don't think that a lot of these people have necessarily ended up getting much money. Like, it's not like we look at them. Oh, see, they've got some ETH, but not much. So, I mean, which is not to devalue the fact that, you know, there are people who've been had money stolen. Crime Enjoyer 2, which is another one. Someone's tried to do some magic around stuff, but really it's just obfuscating what's really happening, which is the same as Crime Enjoyer 1. And you just call the net loser function, and then essentially you set the thief. So it's, again, tries to do stuff, but it's very low tech. Yeah. And someone's deployed Crime Enjoyer to a different address as well. So, and then there's another one, anyone who's got a bit of spare time. This is in here. I think it's unknown or something. Or maybe it was marked as Crime Enjoyer 3. So anyway, so that was one that I thought was worth having a look at. So yeah, so I dare say that that's really disappointing for the people who went to all the effort of creating EIP 7702, that you've got people who, you know, the main users of it pretty much are attackers. But, you know, it offers great possibilities. And so, you know, you could be writing an app and you can think, well, look, I want people to be able to use these capabilities. And so what you can do is you can use the web call ERC, which defines get capabilities and send calls. And it's a way of seeing if the wallet supports 7702, when if it does, using send calls. And I'm pretty sure you can sort of try and prompt MetaMask, maybe using the get capabilities, but they're also working on implementing 7715, and it's going to provide us an explicit API to request permissions for, you know, hey, can you convert it to 7702, and can you do batch transactions? So at the moment, I think you've got the likes of Uniswap, which implement it, and, you know, some other applications, but there aren't many. So in summary, you know, like this EIP 7702 offers great capabilities like multi-call, subscriptions, and stuff like that, and even account upgrade. So it's pretty good. But at the moment, you know, we've got the largest adoption is by criminals, which is really disappointing. But I think it's going to change. So as the use of EIP 7702 you know, becomes more widespread, and as people adopt wallets, you know, that use it, then I think, you know, the risk of being drained goes down. And you know, I mean, so if you're using MetaMask, you're not going to be drained. If you use Ambi, you're not going to be drained. So I think that, you know, the adoption of real wallets is going to increase. And so it means that, you know, you're not going to have to worry about these attackers so much. So 7702 is, you know, going to become ubiquitous, which is good. So the way to make sure that you don't have your wallet drained, I think, is go to WalletBeat, and if your wallet is, say, one of these that doesn't support 7702, get in contact with the dev team and say, hey, you know, are you at least 7702 aware? Will you, you know, block signing any of those type 4 transactions? And if they don't get back to you, I would switch wallets pretty quickly and, you know, not submit any more transactions, because, you know, you might go to a website, you might have a pop-up, and then you might be signing a delegation to some sort of criminal wallet, which would be really bad. So there are some more talks coming up. In particular, next week, there's a recruitment event, and then 2 more talks for the end of the year and some links. So does anyone have any questions?
Yes. Hi, Peter. It's Barry here again.
Yep.
So before, when you were showing us your example code, there was a function in there for verifying the signature that the user had signed the batch or whatever.
Mm-hmm.
What would happen if you didn't verify the signature?
Yeah, if you didn't bother verifying the signature. So this
Yeah,
is
if you didn't, yeah, that's it.
Yeah. So this one here, well, that would then allow anyone to just submit a calls object and say, hey, can we execute this in the context of Barry's EOA? Yeah.
So, oh, you mean if they, I don't understand. So could they execute it in the context of my EOA?
Yeah, because so assuming you've got this delegation set up, then if you don't check the signature here, if you don't check the signature, then it's going to execute. So you remember how TX origin is going to be the smart account, and the smart account is your same address as your EOA. So you're going to execute all these calls in the context of your account address. So if one of these calls was transfer all my ETH to someone else, then it's going to be as if you've signed that transaction, because the assumption is that you're going to check the signature somewhere before you execute it.
Okay. So it would be then the wallet would be the attacker then in that instance, because obviously
The wallet would. Yeah.
that.
Yeah. So you know how we looked at Crime Enjoyer or whatever. So
Yeah.
it's really surprising that they don't have, say, an execute function, a multi-call execute function that doesn't check the signature, as a for instance, because that'd be a really simple way for them to, you'd be able to do a multi-call on some person's wallet and do whatever they can do.
Yeah, cool. Okay. All right. Good. So it's actually up to the wallet provider to implement this, the verification here.
Exactly. And that's why you've got in MetaMask, you've got execute, which is, like making sure it's self, for instance. So, saying that you've submitted the transaction yourself, or it's the 4337 relayer.
I've got one more question.
Yeah, sure.
So you were talking about storage collision, and you suggested that it could maybe be done on purpose.
Yeah.
So how would you do that, and what would it let you do?
All right. So in Ambire, so their code was at entry point marker. So if we copy that, find, and then go down. Actually, no, wrong one. It's at Ambire storage position. That's the one, isn't it? Yeah. So you've got get Ambire storage, and so you've got the nonce, for instance, which is stored at a certain address. And also you've got privileges that are stored at that address. So I imagine that those privileges grant rights to do things. So you could, if you're an attacker and you get someone to so maybe someone uses on one computer, they use Ambire, and then for the same account on a different computer, they use some other wallet that gets hacked into using some exploiter account. they could they could say, hey, this is obviously pointing at the Ambire template contract. So what we're going to do is we're going to muck around with the privileges to allow the attacker to forevermore do stuff. And so that could be something you could maybe do you could set up your attack wallet to use that fact that you know what that address is to do some sort of collision.
Okay. That sounds fairly dangerous.
Yeah, sounds really complicated, but I mean, complexity, if you could steal $1 million, isn't a barrier for most, or for, baddies anyway.
Yeah, well, I'm sure North Korea wouldn't mind just, throwing a few million at the problem.
Well, yeah, I mean, not saying I want attackers to do bad things, and hopefully people from North Korea aren't watching this video. That I think, they should be blocked based on YouTube settings. But, I'm surprised that there aren't some more, like Crime Enjoyer 2 seem really pretty basic. And it feels strange that, there isn't a more competent attack template. That seems actually, I mean, that someone's exploiting it for wallets that, like haven't been updated to this new standard, I can understand. But the fact that there isn't a better attack wallet does seem strange.
Oh, well, give it time.
Yes, things to look forward to. Yeah, yeah. Look, thank you, everyone. Oh, no, actually, are there any more questions? Okay. Well, if not, thank you all for joining today. Have a great rest of your day, and I'll post this on YouTube sometime in the next 24 hours. Okay. And yep, have a great day. Bye-bye.
Bye.
Thank you. Bye.
Thanks.